Hello everyone. Today we are going to solve the governing differential equation of a simply supported beam that is subjected to uniformly distributed load. So let us start the session right away. Just imagine that we have got a simply supported beam. Let me define the geometric properties of the simply supported beam. The first step is you have to define the geometric properties. So this simply supported beam has got a length of magnitude L, as you can see that here. It has got a moment of inertia. When you've got a beam, you don't define the area. Of course, the area is a geometric property, but actually you talk about moment of inertia, which is actually resistance to bending. The unit of moment of inertia is a meter raised to the power 4, or it can be mm raised to the power 4, depending on whatever unit is conducive for you. Okay, now I have clearly defined the geometric properties. Next, I have to define the material property. This beam is made up of material that has got an Young's modulus value of magnitude E. Okay, if you're talking about steel, then you have to substitute the Young's modulus value of steel. If you're talking about aluminum, then you have to substitute the Young's modulus value of aluminum. So it varies from one material to another material. Sometimes, usually people talk about concrete if it is going to be a structure. Fine. Now, what is the stuff that is acting on this beam? As I said, we are going to solve the governing differential equation of a simply supported beam that is subjected to uniformly distributed load. So the stuff that is acting on this beam is a uniformly distributed load. The rate of loading is Q. Its unit is Newton per meter usually. It can be Newton per mm, but let me assume that the unit is Newton per meter. So that is the rate of loading. Okay, now we are going to solve this governing differential equation. So first let me write the governing differential equation for you. It is EI into d raised to the power 4 V by dx raised to the power 4 minus Q naught is equal to 0. Okay, this is the governing differential equation. We have already derived this particular governing differential equation. So if you are curious about how we actually derive the governing differential equation, I highly recommend that you go back and watch that video in order for you to wrap your mind around how we actually derive governing differential equations. So once you have got the governing differential equation, the next step is to define the boundary conditions. So let me define the boundary condition. First boundary condition, that is quite axiomatic, that the left extreme end here, there is not going to be deflection because there is a support there. So displacement at the left extreme end is going to be 0. And what about the right extreme end? Well, there is a support right over there, so the value of displacement at the right extreme end is going to be 0. So these two are boundary conditions right away. Now let me define the third boundary condition. If you draw the bending moment diagram of the simply supported beam, the type of bending moment diagram that you are going to get would look something like this, which means that the bending moment at the left extreme end is going to be 0. The bending moment at the right extreme end is going to be 0. The expression for bending moment is EI into d squared V by dx squared at x is equal to 0 is going to be 0. And the value of bending moment EI into d squared V by dx squared at x is equal to L, that is also going to be 0. So you have got the first boundary condition, displacement at the left extreme end is going to be 0. You have got the second boundary condition, the displacement at the right extreme end is going to be 0. You have got the third boundary condition, that is bending moment at the left extreme end is going to be 0. And also the bending moment at the right extreme end is going to be 0. Now, we are going to solve this differential equation. The first step to solve the differential equation is to assume a trial solution. So let me take a fresh page. The first step is to assume a trial solution. So it is assuming a trial solution. So what is the trial solution that you are going to assume? We are going to assume the trial solution V of x is equal to a naught plus a1x plus a2x square plus a3x cube plus a4x raised to the power 4. I'm going to stop right there. The first question that you may ask is, why do you want to assume a trial solution of order 4, a polynomial trial solution of order 4? The answer is, if you can assume a polynomial trial solution of order 4, which means that you can differentiate this particular trial solution 4 times. So that is clearly the reason why you have to assume a polynomial trial solution of order 4. The reason why you have to assume this particular trial solution is because if you look at the governing differential equation, the continuity that is demanded in the governing differential equation, the order of the governing differential equation is, it is a raised to the power 4. So that is the reason why you have to assume a polynomial trial solution of order raised to the power 4, because it enables you to differentiate the trial solution 4 times. Okay, that's good. The next obvious question is, in the previous problem, we have actually solved this problem of a simply supported beam subjected to uniformly distributed load by assuming a trigonometric trial solution. So we have also assumed a trigonometric trial solution, which would be of something like this: sine pi x over L. Okay, the reason for assuming a trigonometric trial solution, is because the beam mimics a sine wave. So that is so appealing. So we know the reason. The reason for assuming a polynomial trial solution is because we are going to solve this problem by assuming this polynomial trial solution, in which case you are not going to end up with any mathematical error. If you assume trigonometric trial solution, listen to my words very carefully. If you are assuming a trigonometric trial solution, you will end up with mathematical error. You are going to get the value of constant in terms of a variable, which is clearly a mathematical violation. So now you are not going to get any mathematical violation if you assume this particular polynomial trial solution. So it is quite obvious. So I have explained to you the reasons. You will not get any mathematical errors. So the solution that you are going to get in this problem is going to be the exact solution. In the case of trigonometric trial solution, you are not going to get the exact solution. You will be moving towards the exact solution, but you are not going to get the exact solution. So that's the explanation. So what is the second step? The second step is to apply the boundary conditions. So let me write that down here. The second step is apply the boundary conditions. So what are the, sorry about this terrible handwriting. I'll try my best. The second step is to apply the boundary condition. So what is the first boundary condition? The first boundary condition is the value of displacement at x is equal to 0 is going to be 0. Now, if you reflect this particular boundary condition on this particular trial solution, what is that you will be getting? You have to put x is equal to 0. If you put x is equal to 0, the value of displacement should become 0, which means that this term is going to become 0, this term is going to become 0, this term becomes 0, this term becomes 0, and the left hand side also becomes 0, displacement becomes 0. So if you reflect that particular boundary condition, the value of a naught becomes 0. Okay, so that is quite obvious. So that is the first boundary condition. That is what the first boundary condition is. What about the second boundary condition? The second boundary condition is the displacement at x is equal to L is going to be 0. So let me apply the second boundary condition. If we apply the second boundary condition, the value of displacement is going to be 0. And you have to put the value of x as L. Remember, a naught is already 0, so I'm not writing the value of a naught. I will start with a1 L plus a2 L square plus a3 L raised to the power 3 plus a4 L raised to the power 4. So that is what the second boundary condition is. Okay, now let me write the third boundary condition. The third boundary condition is the value of bending moment, which is ei into d squared v over dx square at x is equal to 0 is going to be 0. I can rewrite this particular boundary condition. You see, you take this ei to the right hand side, it just disappears, it just vanishes. So what is that you are going to get? You are going to get d squared v by dx square. Okay. At x is equal to 0 is equal to 0. That is the third boundary condition. Let me take a fresh page now. Yes. So let me take this third boundary condition to the next step. What is demanded in the third boundary condition is you have to find the value of d squared v by dx squared. Go ahead and find the value of d squared v by dx squared. You just have to differentiate this particular triangle solution 2 times. Right away, I'm going to do that. See, you should be able to differentiate the triangle solution 2 times. So let me write what you are going to get if you differentiate the triangle solution to get the value of d squared v by dx squared. So one by one, if you differentiate a naught 2 times, that becomes 0. If you differentiate a1x 2 times, that becomes 0. If you differentiate a2x squared, here we go, let me use this blue. If you differentiate this a2x squared, what is that you are going to get? One time differentiation is going to give you 2a2x, 2 times differentiation is going to give you 2a2. So let me write that here, 2a2. And look, if you differentiate a3x cubed, 1 time differentiation is going to give you 3a3x squared, 2 times differentiation is going to give you 6a3x. So let me write that here, it is plus 6a3x. And a4x raised to the power 4. 1 times differentiation is going to give you 4a4x cubed. 2 times differentiation is going to give you the value as 12a4x squared. So that's it. Plus 12a4x squared. Now I can apply the boundary conditions. What happens at x is equal to 0? At x is equal to 0, d squared v by dx squared becomes 0. So this term becomes 0. And at x is equal to 0, this term becomes 0, this term becomes 0. You are going to get the value of a2 is 0. That is quite axiomatic. So I got the value of a2 by applying the third boundary condition. So let me write the fourth boundary condition. The value of d squared v by dx squared at x is equal to L is going to be 0. So that is what the fourth boundary condition is saying, which means that the left hand side, obviously that becomes 0. D squared v by dx squared, that is 0, is equal to 2a2. a2 is already 0, so I'm not going to write that value here. So plus 6a3L, because I'm talking about the location, I'm concerned about the location at x is equal to L, plus 12a4L square. So that's what you will be getting. Now you can divide this equation by 6L. So what is that you will be getting? If you divide this equation by 6L, both on the left hand side and the right hand side is 0. 0 by anything is 0. If you divide by 6L, you will be getting a3. You divide this 12 by 6, you are going to get 2a4. If you divide this L square by L, you get L. So I'm getting a relationship between a3 and a4. So a3 is equal to minus 2a4L. So I got the relationship between a3 and a4. So you see, already by applying the boundary conditions, we are able to get the value of a naught. By applying the boundary condition, we are able to get the value of, you see, we are able to get the value of a2. Yes. And we can get the value of a3 in terms of a4. So what I'm going to do in the next step, since I know the combination of all these values, I'm going to modify the triangle solution a little bit. I'm going to rewrite the triangle solution in terms of known values. So allow me to rewrite the triangle solution. Let me take a fresh page now. So rewrite the triangle solution. V of x is equal to a naught is 0 plus a1x, we don't know the value of a1 yet, we don't know, and the value of a2 is 0, okay, fine, and the value of a3, you see, it is minus 2a4L, so it is plus a3, which is minus 2a4L into x square, right? I'm sorry, a naught plus a1x plus a2x squared plus a3x cubed, so it is x cubed plus a4 x raised to the power 4. So that is the modified triangle solution. So all I need to know is the value of a1 and a4. Once I get the value of a1 and a4, I am done. So I can rewrite this equation as v of x is equal to a1x. I can take this a4 common outside. So let me take this a4 common outside. So what is that you will be getting? You are going to get x raised to the power 4 minus 2lx cubed. So that is the value of v of x. So that is the value of v of x. Okay, I got it. So that is our new modified trial solution. All I need to know is two values. If I know the value of a1 and a4, I can tell what is the value of displacement at any position. Okay, in the next step, I think it is step number 4. This is step number 3. You see, step number 1 is to assume a trial solution. Step number 2, you apply the boundary conditions. And in step number 3, you modify the trial solutions, right? And in step number 4, you are going to find the value of d raised to the power 4 v by dx raised to the power 4. So find d raised to the power 4. You have to differentiate this equation 4 times. If you differentiate the first term 4 times, obviously you are going to get 0. If you differentiate this term 4 times, of course you are also going to get 0, because the order is 3. You cannot differentiate it 4 times. You will get 0. But what happens if you differentiate x power 4 times? What happens if you differentiate x power 4 times? 1 time differentiation is going to give you 4x cubed. 2 times differentiation is going to give you 12x squared. 3 times differentiation is going to give you 24x. 4 times differentiation is going to give you the value as 24. So the value is 24. Already there is an a4 sitting there. So I have kind of retracted that 24 outside. So it gives 24a raised to the power 4. I'm sorry, 24a4. Okay, step number 5. You have got d power 4v by dx power 4. You take this value, substitute the value of d power 4v by dx power 4 in the governing differential equations, GDE. It is an acronym for governing differential equation. So you take this value of d power 4v by dx power 4, and all you have to do is go ahead and put it here. You know, mathematics is just like moving objects. You take that and you put it here. What is that you will be getting? So I will take a fresh page. Give me a second. So it is EI into d power 4v by dx power 4. That is 24a4 minus q naught is equal to 0. Get the value of a4. a4 is equal to q naught divided by 24ei. I have got the value of a4. I have got the value of a4. Now all I need to know is I need to know the value of a1. That's it. All I need is I need to know the value of a1. So what is the value of a1? Right? So you look at this particular equation. I want you to localize your attention on this particular equation. Let us see whether we can squeeze out the value of a1 from this equation. Okay, we know that the value of a2 is 0, so this term becomes 0. And we know the value of a3 in terms of a4, right? So, okay, now let us do this. So if you look at that particular equation, so 0 is equal to, if you look at this particular equation, 0 is equal to a1l. That equation is obtained by substituting the second boundary condition, a1l. And you see that you know the value of a3 in terms of a4. So that is what that you know already. What is the value of a3 in terms of a4? Well, you have this equation. a3, if you substitute in terms of a4, you will be getting a4x power 4 minus 2lx cubed. But you are talking about the location at x is equal to l. So what happens is it is a4 plus a4 into x raised to the power 4. No, it is not x raised to the power 4, because we are talking about at the location at x is equal to l. So what happens is it is l raised to the power 4 minus 2lx cubed. But you have to put x is equal to l, so that becomes minus 2l raised to the power 4 minus 2l raised to the power 4. So that's it. That's it. So what is that you will be getting? In the next step, it is equal to a1l. The value of a4 is q naught divided by 24ei into minus l raised to the power 4. Okay, what is that you will be getting in the next step? you will get the value of A1. So what is the value of A1? So the value of A1 is Q naught L cube divided by 24 EI. That is the value of A1. So you look at the modified trial solution. In the modified trial solution, we have got the value of A1 and we have also got the value of A4. So all you have to do is go ahead and substitute the value of A1 and A4 in this particular trial solution. The problem is over. So let me do that in the next step. Go ahead and substitute the value of A1 and A4 in the modified trial solution. V of x is equal to, what is the value of A1? It is Q naught L cube divided by 24 EI. It is V of x is equal to, A1 is Q naught L cube divided by 24 EI. A1x, okay, fine, plus A4. And what is the value of A4? It is plus A4 x power 4 minus 2L x cube. That's A4 x power 4 minus 2L x cube. But in a moment, I will be substituting the value of A4. And we know what is the value of A4. It is here. It is Q naught divided by 24 EI. It is Q naught divided by 24 EI. So go ahead. It is Q naught divided by 24 EI. So that is our solution. Okay. Just to find out whether the solution is correct or not, just we can compare this particular solution to the famous formula that you might remember. Now, all I have to do is the maximum deflection occurs at x is equal to L by 2. So what happens to this particular equation at x is equal to L by 2? In other words, what is the value of displacement at x is equal to L by 2? What happens? So if you substitute the value of x is equal to L by 2, what happens is it becomes Q naught L raised to the power 4 divided by 48 EI. So that is what you will be getting. Plus Q naught divided by 24 EI. All you have to put is x is equal to L by 2. If you substitute x is equal to L by 2, it is L raised to the power 4 divided by 16 minus 2 into L raised to the power 4 divided by, what happens, what is that you are going to get in the denominator? It is 2 raised to the power 3. That becomes 8. Let us do it. I'm sorry about this discontinuity, right? Okay, we are going to do this. It is Q naught L raised to the power 4 divided by EI. I'm going to take it outside. So what is that you will be getting? You are going to get, if you take it outside, you will be getting 1 by 48 is here, plus 1 divided by, what is this, 24 into 16? 24 into 16 is 384, right? Minus 2 divided by, what is this, 24 into 8? It is 192. 192. Okay. Now we are going to take LCM and we are just going to complete this problem. Looks complex, but actually it is not. It is actually very simple. So I have taken a fresh page. So follow from this particular step. It is Q naught L raised to the power 4 divided by EI. If you take the LCM and if you simplify this, I'm going to write the answer right away. If you take the LCM, it is 48 into 8 is 384. So that is 8. You take the LCM, plus 1 minus 4 divided by 384. That gives 5 by 384 into Q naught L raised to the power 4 divided by EI. I am quite excited about this answer. This is deflection at x is equal to L by 2, which means at the center. The reason why I'm excited about this answer is because it is the same as the answer that you get in strength of materials, which is the exact solution. So we have solved this problem by exact solution. All I'm interested in knowing is what is the value of 5 by 384? It is 0.01302 Q naught L raised to the power 4 divided by EI. The reason why I have to bother about these decimals is because if you solve the same problem by Galerkin's weighted residual method, the answer that you are going to get is 0.01307 Q naught L raised to the power 4 divided by EI, that is at the center. So this is by Galerkin's. Remember, it is Galerkin's weighted residual method that actually gives birth to the concept of finite element analysis, right? So Galerkin's weighted residual method, you can see from this result that it goes hand in hand. It goes shoulder to shoulder with the exact method. So it sort of reaches the exact solution in an asymptotic manner. Okay, fine. Now, what is the error? What is the error at the center of the beam by using Galerkin's weighted residual method? So let us calculate that. So let me take a fresh page. So the percentage error, the formula is, it is the true value minus the value that is obtained by Galerkin's weighted residual method. So I will write that as Galerkin's value divided by true value. If you want to find the percentage, you have to multiply this by 100. And what is the true value? It is 0. Okay, I have written that here. The true value is 0.01302. 0.01302. The value obtained by Galerkin's method is 0.01307 divided by the true value is 0.01302, right, into 100. You don't have to bother about the negative sign because all you were interested in finding out is the difference between the true value and the Galerkin's value. So if you solve this, you will be getting 0.37. So approximately it is 0.38%. So the error at the center of the beam by using Galerkin's method is 0.38%. Remember, we have already solved this problem by using Galerkin's weighted residual method, right? By assuming a trigonometric trial solution, we have solved this problem by Galerkin's weighted residual method. So look how powerful this Galerkin's weighted residual method actually is. The error is only 0.38%. So it is the piecewise extension of Galerkin's weighted residual method that actually gives birth to the concept of finite element analysis. So please wait. We are going to see what is piecewise extension of Galerkin's weighted residual method in the next video. Thank you all for your patience. Radiate hope and do amazing work. Thank you.